Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1926. Erwin Schrödinger, grappling with the nascent field of quantum mechanics, found himself wrestling with a seemingly paradoxical interpretation of matter. He envisioned electrons, the fundamental building blocks of atoms, as waves, a concept that had emerged from the work of Louis de Broglie. However, the mathematical framework to accurately describe these waves and their behavior within the atom remained elusive. Schrödinger's initial attempts, though brilliant, were hampered by relativistic considerations, leading to equations that, while elegant, did match experimental results. He had to find a way to reconcile the wave-like nature of particles with the observed discrete energy levels of atoms, a significant problem that challenged the very foundations of physics. This challenge, the need for quantum mechanical description of atomic phenomena that surpassed the limitations of the prevailing Bohr model, ignited Schrödinger's genius. The Bohr model, while a pivotal step forward, presented a patchwork of ad hoc rules and assumptions. It described the electrons orbiting the nucleus in specific, quantized energy levels, but it offered no clear explanation for why these energy levels existed, or for the underlying mechanisms governing atomic stability. Schrödinger sought a more fundamental, more complete, and more mathematically rigorous framework. His solution, a stroke of theoretical brilliance, was the development of the Schrödinger equation. This equation, expressed in two primary forms, time-dependent and time-independent, provided a complete description of the evolution of quantum systems. The time-dependent Schrödinger equation, a partial differential equation, describes how the wave function of a quantum system changes over time. It's a fundamental equation in quantum mechanics, analogous to Newton's second law in classical mechanics. The time-independent version, on the other hand, is used to determine the stationary states of a system, the states with definite energy. The equation's power resided in its ability to precisely predict the quantized energy levels of atoms, a critical advance. The mathematical tools Schrödinger employed were sophisticated, drawing upon the conceptual frameworks of classical mechanics, wave theory, and differential equations. At the heart of his formalism lies the Hamiltonian operator, representing the total energy of the system. This operator acts on the wave function, a mathematical function that describes the probability amplitude of finding a particle in a given state. The wave function, a solution to the Schrödinger equation, contains all the information we can know about a quantum system, including its energy, momentum, and spatial distribution. A particularly compelling example of Schrödinger's work, and a testament to its predictive power, is the solution of the Schrödinger equation for the hydrogen atom. By applying the equation to this simplest of atomic systems, Schrödinger was able to calculate the energy levels of the electron, precisely matching the experimental observations. This success offered conclusive evidence of the validity of his approach, and it provided a profound understanding of atomic structure, the very basis of all matter. The solution yielded the same results that experiments had already established, but it did so from first principles, offering a theoretical framework that was both elegant and predictive. The discrete energy levels, the very essence of the quantum nature of the atom, emerged naturally from the mathematical solution. The impact of the Schrödinger equation on modern science continues to be profound. It remains a cornerstone of quantum mechanics, a tool used daily by researchers. In computational chemistry, the Schrödinger equation, or approximations of it, is used to model the behavior of molecules, predict chemical reactions, and design new materials. In materials science, it helps us understand the electronic properties of solids, leading to advances in semiconductors, superconductors, and other technologies. In condensed matter physics, the equation is used to study the behavior of matter at different temperatures and pressures, revealing the underlying principles that govern the physical world. Schrödinger's work was directly influenced by the hypothesis proposed by Louis de Broglie. De Broglie had suggested that matter, like light, possesses both wave-like and particle-like properties. This concept, a radical departure from classical physics, provided the essential foundation upon which Schrödinger built his wave mechanics. De Broglie's idea of matter waves, a previously unseen connection between particles and waves, gave Schrödinger the conceptual framework he needed to formulate his equation. These waves, he realized, could be described mathematically, and their behavior would govern the characteristics of matter at the atomic level. The influence of the Schrödinger equation extended far beyond its initial application. It shaped the development of quantum chemistry, a field that applies quantum mechanics to the study of chemical systems. The equation provided the theoretical basis for understanding molecular structure, chemical bonding, and reaction mechanisms. It also influenced the development of our understanding of molecular structure and enabled the prediction of the properties of molecules and materials. The equation's impact is evident in the tools and techniques used by chemists and materials scientists worldwide. The Schrödinger equation also profoundly influenced the development of quantum field theory, the theoretical framework that combines quantum mechanics with special relativity. Quantum field theory provides a more complete description of the fundamental forces of nature, including electromagnetism, the weak force, and the strong force. The concepts and mathematical tools developed by Schrödinger, such as the wave function and the Hamiltonian operator, provided the foundation for the development of quantum field theory. His work, therefore, set the stage for some of the most significant scientific advances of the 20th and 21st centuries. The mathematical formalism underpinning Schrödinger's equation represents a pivotal achievement, transforming the nascent field of quantum mechanics into a rigorous, predictive science. The intellectual problem Schrödinger addressed centered on the need for a stable, stationary state description of quantum systems. Prior to his work, the quantum world, while demonstrating peculiar behaviors, lacked a coherent mathematical framework to describe these systems' intrinsic properties, particularly their energy levels. His solution, elegant in its simplicity, involved framing the behavior of quantum particles as an eigenvalue problem for a specific operator, the Hamiltonian. The Hamiltonian operator, a mathematical construct representing the total energy of a system, became the central figure. Schrödinger proposed that the possible energy states of a system could be determined by solving the equation the Hamiltonian operator acting on the wave function equals the energy eigenvalue multiplied by the wave function. This equation, often referred to as the time-independent Schrödinger equation, is expressed as H operating on psi equals E multiplied by psi. Here, H represents the Hamiltonian operator, psi denotes the wave function, and E signifies the energy eigenvalue. Each solution to this equation, That is, each specific wave function and its corresponding energy value represents a possible stationary state of the system. The mathematical tools employed were those of linear algebra and operator theory, concepts then being actively developed and refined. Schrödinger drew heavily on the work of David Hilbert, particularly Hilbert's investigations into the mathematical foundations of quantum mechanics. Hilbert's exploration of Hilbert spaces, abstract vector spaces equipped with an inner product, provided the mathematical framework for understanding the space of possible wave functions. The wave function, psi, resides within this Hilbert space, and the Hamiltonian operator acts upon it, transforming it. The solutions to the Schrödinger equation, the energy eigenstates, are the eigenvectors of the Hamiltonian operator. The corresponding energy values, the eigenvalues, are the system's possible energy levels. Boundary conditions, specific constraints imposed on the wave function at the boundaries of the system, became a crucial element. These conditions, dictated by the physical nature of the system, determined the allowed solutions to the Schrödinger equation. They ensured that the wave function remained well-behaved, physically meaningful, and provided the necessary constraints to quantize the energy levels. A classic example, the particle in a box problem, illustrates this principle. Consider a particle confined to a one-dimensional region, a box with impenetrable walls. The potential energy inside the box is zero, while outside, it is infinite. The wave function, therefore, must vanish at the walls of the box. Solving the Schrödinger equation with these boundary conditions results in a set of allowed wave functions, each corresponding to a specific energy level. The energy levels are quantized, meaning the particle can only possess specific, discrete energy values, a direct consequence of the boundary conditions. The physical interpretation of the wave function is central to understanding Schrödinger's framework. The square of the absolute value of the wave function at a given point in space provides the probability density of finding the particle at that point. This probabilistic interpretation, a radical departure from classical physics, dictates that we can only determine the probability of finding a particle at a specific location rather than predicting its exact position. The wave function, therefore, is a mathematical representation of the particle's state, providing a probabilistic description of its location and other measurable properties. The impact of the boundary conditions cannot be overstated. These conditions, derived from the physical constraints of the system, dictate the nature of the solutions. They are the mechanism by which energy is quantized, generating the discrete energy levels observed in quantum systems. Changing the boundary conditions, for example, altering the shape of the box in the particle in a box problem, leads to different sets of allowed wave functions and energy levels. This demonstrates the intimate connection between the physical environment and the quantum behavior of the system. The mathematical framework established by Schrödinger, with its focus on the eigenvalue problem, established a robust foundation for quantum mechanics. This framework provided the tools necessary to calculate the energy levels, wave functions, and other properties of quantum systems. Its influence extended far beyond the initial problem of understanding atomic spectra. The work of David Hilbert, particularly his development of Hilbert spaces and operator theory, directly influenced Schrödinger's approach. Hilbert's focus on rigorous mathematical foundations, his development of abstract vector spaces, and his exploration of operators provided the necessary mathematical tools and conceptual framework for Schrödinger's work. The eigenvalue problem, central to Schrödinger's equation, is a direct application of Hilbert's operator theory. This mathematical framework, in turn, exerted a profound influence on subsequent generations of scientists. It provided the essential mathematical tools for understanding atomic and molecular structure. It allowed for the calculation of the properties of atoms, molecules, and materials, enabling the development of quantum chemistry. The ability to predict the behavior of these systems, based on fundamental principles, revolutionized chemistry and materials science. The influence extended to the development of computational chemistry, which relies on solving the Schrödinger equation for increasingly complex systems. The enduring relevance of the eigenvalue problem, as formulated by Schrödinger, is undeniable. It remains the cornerstone of quantum mechanics, underpinning many of the computational techniques used in modern physics, chemistry, and materials science. The ability to solve the Schrödinger equation, or approximate its solutions, remains a central goal of theoretical and computational science. The concepts of energy eigenstates and eigenvalues, derived from Schrödinger's work, continue to shape our understanding of the quantum world. The framework he established provided the necessary tools to understand the structure and behavior of matter at the atomic and molecular level, paving the way for countless technological advancements. The initial successes of the Schrödinger equation in describing simple systems, such as the particle in a box and the harmonic oscillator, were profoundly significant. The limitations, however, quickly became apparent. Real-world physical systems rarely exhibit such ideal behavior. Atoms, molecules, and condensed matter systems presented a formidable challenge. The exact solutions to the Schrödinger equation for these systems proved elusive, necessitating the development of approximation methods. This marked a crucial transition in Schrödinger's work, moving from the elegant simplicity of exact solutions to the pragmatic realm of approximate techniques. The intellectual problem Schrödinger confronted was the need to extend his equation to more complex and realistic physical scenarios. He, along with his contemporaries, recognized that the straightforward application of the equation, as demonstrated in simpler cases, would frequently yield intractable mathematical problems. The goal was to develop methods that could provide reliable approximations to the solutions, allowing for the prediction of observable quantities such as energy levels, transition probabilities, and the spatial distribution of electrons. This required a shift in focus from seeking perfect solutions to developing tools that could provide accurate estimates, even when exact solutions were unobtainable. Schrödinger's approach to this problem involved several key mathematical techniques. Foremost among these were perturbation theory and variational methods. Perturbation theory, both time-independent and time-dependent, offered a systematic way to approximate the solutions to the Schrödinger equation when the system's Hamiltonian could be divided into a solvable part and a small perturbation. The solvable part, representing the system's behavior in the absence of the perturbation, provided a foundation for understanding, while the perturbation accounted for the added complexity. Variational methods, on the other hand, provided a framework for finding the best possible approximation to the ground state energy of a system. These methods involved constructing a trial wave function, parameterized by adjustable parameters, and minimizing the energy expectation value. The parameters that minimized the energy then defined the best approximation to the ground state. The application of these methods required sophisticated mathematical tools. In the case of the harmonic oscillator, which, while exactly solvable, served as a crucial model for understanding vibrational motion in molecules, Schrödinger's work made made clear the use of Hermite polynomials. These orthogonal polynomials, solutions to the differential equation associated with the harmonic oscillator, provided a complete set of basis functions for describing the quantum states of the system. For the hydrogen atom, Schrödinger's equation demanded the use of spherical coordinates and the separation of variables. This led to the identification of spherical harmonics, solutions to the angular part of the equation, which described the spatial distribution of the electron's angular momentum. The radial part of the equation then could be solved to determine the energy levels and radial wave functions. Specific, tangible examples of Schrödinger's work and its direct applications are abundant. Consider the harmonic oscillator. While an idealized model, it provided a crucial foundation for understanding vibrational motion in molecules. By applying perturbation theory to the harmonic oscillator, one could account for small deviations from the ideal behavior, such as anharmonicity, which is a deviation from perfect harmonic motion. The hydrogen atom, a cornerstone of quantum mechanics, provided a rigorous test of Schrödinger's equation and its associated methods. The exact solution for the hydrogen atom, obtained by separating variables in spherical coordinates, yielded the energy levels and wave functions. These results were in perfect agreement with experimental observations, providing strong validation of the theory. The application of perturbation theory to the hydrogen atom, accounting for the effects of external fields or relativistic corrections, further demonstrated the power of these methods. The influence of earlier mathematical work was evident in Schrödinger's methods. The use of perturbation theory, for example, drew upon the mathematical techniques developed earlier in the 19th century, particularly by mathematicians like Carl Jacobi in the context of solving differential equations. Jacobi's work on the theory of differential equations, including the development of methods for finding solutions to linear differential equations with variable coefficients, provided a foundation for the techniques that Schrödinger and others would later employ in quantum mechanics. The use of special functions, such as Hermite polynomials and spherical harmonics, was also rooted in the earlier work of mathematicians who had studied these functions extensively. The impact of Schrödinger's work on other scientists and the development of subsequent research was profound. The methods he pioneered became foundational for computational chemistry. The ability to solve the Schrödinger equation or approximate its solutions for increasingly complex systems enabled chemists to calculate molecular properties, predict reaction rates, and design new materials. The development of quantum chemical software packages, such as Gaussian and Gamis, relied directly on the methods developed by Schrödinger and his contemporaries. These programs allow scientists to perform calculations on molecules of increasing size and complexity, providing insights into their behavior and properties. The application of these methods extended beyond chemistry. In condensed matter physics, perturbation theory and variational methods are essential tools for understanding the behavior of electrons and solids, predicting the properties of materials, and designing new electronic devices. The modern relevance of these approximation methods is substantial. Perturbation theory and variational methods remain essential tools in quantum chemistry, condensed matter physics, and other areas of science. They provide the framework for understanding the behavior of complex quantum systems from molecules to solids. The use of these methods continues to be refined and extended, with new algorithms and computational techniques constantly being developed. The concepts of energy eigenstates and eigenvalues derived from Schrödinger's work continue to shape our understanding of the quantum world. The framework he established provided the necessary tools to understand the structure and behavior of matter at the atomic and molecular level, paving the way for countless technological advancements. The enduring legacy of Schrödinger's work lies in its ability to provide a powerful and versatile framework for understanding the behavior of matter at the quantum level. The methods he developed and the concepts he introduced continue to shape our understanding of the world around us. Having established the fundamental principles of quantum mechanics and its application to atomic phenomena, Schrödinger's attention shifted towards a profound challenge, reconciling the theory with the principles of special relativity. The existing Schrödinger equation, while remarkably successful in describing the behavior of non-relativistic particles, faced significant limitations when applied to systems moving at speeds approaching that of light. The core issue lay in the treatment of energy and momentum. Special relativity, formulated by Albert Einstein, dictated that energy and momentum are inextricably linked, forming components of a four-dimensional spacetime framework. The original Schrödinger equation, rooted in Newtonian mechanics, failed to account for these relativistic effects. This prompted Schrödinger to embark on the development of relativistic wave equations. His ambition was to create a mathematical framework that accurately described the behavior of quantum particles, taking into account the principles of special relativity. This quest, however, proved to be exceptionally complex, and Schrödinger's initial attempts led him to the Klein-Gordon equation, an equation that, while carrying his name, was also independently developed by others, including Oscar Klein and Walter Gordon. The Klein-Gordon equation, in its essence, is a relativistic wave equation that describes the behavior of spin-zero particles, such as the pion. It builds upon the foundation of the Schrödinger equation, but it incorporates the relativistic energy-momentum relation derived from Einstein's famous equation, E equals mc squared. The equation utilizes four vectors, mathematical objects that combine spatial and temporal components, to describe the particle's position and momentum in space-time. The use of these mathematical tools served to ensure that the equation was consistent with the principles of special relativity. The Klein-Gordon equation takes the form of a second-order partial differential equation. The equation can be written as the D'Alembert operator, acting on a field equal to a constant times the field itself. The D'Alembert operator, a relativistic generalization of the Laplacian operator, incorporates both spatial and temporal derivatives. This mathematical structure reflects the interplay between space and time, a central tenet of special relativity. The solutions to the Klein-Gordon equation represent the wave function of a relativistic particle, and the square of the wave function provides a probability density. A significant aspect of the Klein-Gordon equation is its prediction of both positive and negative energy solutions. These negative energy solutions presented a perplexing challenge. In classical physics, energy is typically considered to be a positive quantity. The existence of negative energy solutions appeared to suggest the possibility of particles with negative mass, a concept that seemed to defy physical intuition. This puzzle was later resolved through the development of quantum field theory, which reinterpreted the negative energy solutions as representing antiparticles, such as the positron, the animated counterpart of the electron. The Klein-Gordon equation's impact extended beyond the realm of theoretical physics. It served as a crucial stepping stone in the development of quantum field theory, a theoretical framework that describes the behavior of particles in fields at the quantum level, incorporating both quantum mechanics and special relativity. The equation provided a foundation for understanding the creation and annihilation of particles, processes that are fundamental to many physical phenomena, including particle interactions and the behavior of the early universe. The development of relativistic quantum mechanics was significantly influenced by the work of Max Planck, whose introduction of the concept of energy quantum laid the groundwork for quantum theory. Planck's work established the idea that energy is not continuous, but rather exists in discrete packets or quanta. This revolutionary concept, later refined by Niels Bohr and others, provided the foundation upon which Schrödinger built his own work. Furthermore, Albert Einstein's theory of special relativity, which demonstrated the equivalence of mass and energy in the interconnectedness of space and time, directly informed Schrödinger's efforts to develop a relativistic wave equation. Einstein's insights into the nature of spacetime and the behavior of objects at high speeds were essential for understanding the limitations of the original Schrödinger equation and for guiding the development of a more comprehensive relativistic framework. The Klein-Gordon equation, while not without its limitations, exerted a profound influence on subsequent generations of physicists. One of the most notable examples of this influence is the Dirac equation, developed by Paul Dirac. The Dirac equation, a relativistic wave equation for spin 1/2 particles, such as electrons, built upon the foundation established by the Klein-Gordon equation. Dirac, inspired by the Klein-Gordon equation's incorporation of relativistic principles, sought a first-order equation which led him to predict the existence of antimatter. The Dirac equation, a landmark achievement in theoretical physics, is still used today to describe the behavior of electrons and other fundamental particles. The development of quantum field theory, which is fundamental to modern particle physics, was also significantly impacted by the Klein-Gordon equation. The equation provided a critical framework for understanding the behavior of relativistic particles and paved the way for the development of concepts such as particle creation and annihilation. The techniques and conceptual frameworks developed in the context of the Klein-Gordon equation were later extended and refined to describe a wide range of physical phenomena, from the interactions of elementary particles to the behavior of the early universe. The Klein-Gordon equation, while describing the behavior of spin-zero particles, served as a crucial precursor to the development of more complex and versatile relativistic quantum mechanical theories. While it has limitations and is no longer the central equation in modern particle physics, its historical significance is undeniable. It represents a vital step in the journey towards a complete and coherent understanding of the quantum world, a journey that continues to this day. The equation's legacy is seen in the ongoing refinement of quantum field theory and its application to a wide range of physical problems, including the study of the fundamental forces of nature and the behavior of matter at the highest energies. The Klein-Gordon equation's enduring influence underscores the importance of Schrödinger's contributions to the development of quantum mechanics and his unwavering commitment to understanding the fundamental laws of physics. The Schrödinger equation, born from a period of profound intellectual ferment, continues to resonate throughout the scientific landscape, a testament to its enduring explanatory power. Its impact extends far beyond the confines of atomic physics, shaping our comprehension of reality at its most fundamental level. The equation's significance lies not only in its ability to accurately predict the behavior of quantum systems, but also in the conceptual revolution it ignited, challenging long-held assumptions about the nature of the physical world. The very essence of Schrödinger's contribution lies in providing a mathematical framework for understanding the wave-like properties of matter, a concept that had previously lacked a rigorous theoretical foundation. The earlier work of Louis de Broglie, proposing that matter, like light, possessed both wave-like and particle-like characteristics, created a crucial precursor. De Broglie's hypothesis, suggesting that every particle could be described by a wave, provided a critical insight. Schrödinger, building upon this foundation, developed a precise mathematical description of these matter waves. His equation, a second-order partial differential equation, offered a means to calculate the evolution of a quantum system over time, allowing physicists to predict the probability of finding a particle in a given location. The power of the Schrödinger equation quickly became apparent. It provided a remarkably accurate description of the hydrogen atom, a feat that earlier models, such as Niels Bohr's, had struggled to achieve. The equation's ability to explain the observed spectral lines of hydrogen, a fundamental property of the atom, was a resounding success. This triumph solidified its place as a cornerstone of quantum mechanics and provided the initial, crucial evidence for its validity. The equation's success extended beyond hydrogen, providing a framework for understanding the behavior of more complex atoms and molecules. The impact of the Schrödinger equation extends far beyond the realm of theoretical physics. Its influence is felt in numerous scientific disciplines. In chemistry, it forms the basis for understanding chemical bonds and reactions. Quantum chemistry, a field that relies heavily on the Schrödinger equation, allows researchers to predict the properties of molecules, design new materials, and understand complex chemical processes. This ability has revolutionized fields such as materials science, drug discovery, and environmental science. Its influence is also seen in solid-state physics, where it is used to describe the behavior of electrons in solids, leading to the development of semiconductors, transistors, and other essential components of modern technology. These applications, born from the initial theoretical framework, demonstrate the equation's practical significance. The development of the Schrödinger equation also prompted intense philosophical debate. It challenged the classical view of a deterministic universe, where the future is entirely determined by the present. The equation, with its inherent probabilistic nature, suggested that the universe operates on a fundamentally uncertain level. The act of measurement, according to the Copenhagen interpretation, introduced a disturbance that altered the system. This challenged the long-held belief in objective reality. The measurement problem, the question of how the wave function collapses upon measurement, has continued to be a subject of debate among physicists and philosophers. The equation, therefore, not only revolutionized physics, but also prompted profound questions about the nature of reality and our place in the universe. The development of the Schrödinger equation was directly influenced by the work of several individuals. Max Born, for example, provided a crucial interpretation of the wave function, suggesting that its square represents the probability density of finding a particle at a given location. This probabilistic interpretation was pivotal to the the equation's acceptance and application. Werner Heisenberg's development of matrix mechanics, an alternative formulation of quantum mechanics, albeit mathematically equivalent to Schrödinger's wave mechanics, also influenced the development of the equation. The interaction between these differing approaches helped to clarify the underlying principles of quantum mechanics. The influence of these colleagues in the collective intellectual effort during this period underscores the collaborative nature of scientific progress. The Schrödinger equation, once formulated, directly influenced the work of numerous scientists. Carl Dirac, for instance, built upon Schrödinger's work to develop a relativistic version of the equation, which incorporated the principles of special relativity. Dirac's equation, a significant advancement, was essential for describing the behavior of high-energy particles and for understanding the existence of antimatter. The development of Dirac's equation demonstrates the direct influence of Schrödinger's work on subsequent advances in quantum mechanics. The equation also influenced the development of quantum field theory, a framework that describes the interactions of particles and forces. The creation of quantum field theory, which relies on the principles established by Schrödinger, represents a further expansion of his initial insights. The legacy of the Schrödinger equation is seen in its continued use in various scientific disciplines. It remains a fundamental tool for understanding the behavior of quantum systems. The equation's influence is also seen in the development of advanced computational methods, which allow scientists to solve the equation for increasingly complex systems. These computational methods, now essential tools in many areas of science and engineering, are a direct consequence of Schrödinger's initial work. The equation's continued relevance in contemporary science and its ongoing influence on research and technology demonstrates its enduring impact. The very act of formulating the equation and the paradigm shift it created continues to shape the way we think about the physical world. The equation forced scientists to abandon classical notions of determinism and embrace the probabilistic nature of quantum mechanics. This shift in perspective has had a profound impact on our understanding of reality. The equation's influence is also seen in the development of new technologies, such as lasers and transistors, which rely on the principles of quantum mechanics. These technologies, which have transformed our world, are a direct consequence of Schrödinger's groundbreaking work. The journey of Erwin Schrödinger, from his initial conceptual breakthroughs to the equation's widespread application, offers a compelling example of the scientific process. His dedication to understanding the fundamental laws of nature and his willingness to challenge established ideas are a source of inspiration for scientists. His equation, a testament to his intellectual prowess, continues to shape our understanding of the universe. Its enduring influence underscores the importance of Schrödinger's contributions and serves as a reminder of the power of human curiosity and a relentless pursuit of knowledge. The Schrödinger equation is more than a mathematical formula. It is a window into the quantum world, a testament to human ingenuity, and a cornerstone of modern science. It remains, even today, an essential tool for understanding the universe at its most fundamental level. Schrödinger's legacy is, therefore, an ongoing exploration of the very fabric of reality itself.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.